All right. So we're going to be talking about transformations today, okay? And then we're going to be performing one type of transformation. So when we talk about transformations, transformation is the movement from one object from one place to another, okay? Now we could do that several different ways. We could do that by sliding it, reflecting it, rotating it, or dilating it, okay? So we can do that 4 different ways. Sliding it, rotating it, dilating it, or reflecting it. So an image, what is an image? The image is the figure after the transformation. So on your paper, you want to make sure and fill in the blanks as we go through. The image is the figure after the transformation. If you look at this, here is the pre-image, here is the image, okay? The pre-image is the one before the transformation. So pre-image is the figure prior to the transformation, prior to the move. Who in here has ever seen, and I know you have, Transformers? Okay? So Transformers change, right? They change or they move, right? They turn into something else sometimes. Okay? They're going to a different place. So they transform, right? Transform. So we're doing transformations. Isometry. So isometry is a transformation that preserves congruency. Okay? Preserves congruency. In other words, a transformation in which the image and pre-image have the same side lengths and angle measurements. The following transformations maintain their mathematical congruency. Okay? So there are transformations that we have that are not isometry, that do not maintain their same size and shape. Okay? And then there's others that do. So we have the rotation. Okay, rotation, and the angle of rotation is called the amount of rotation about a fixed point. So this is the angle of rotation. Okay, and think of that as a clock, right? If you look at a clock and you go, all right, from 12 to 9, that's 45 degrees, right? From 12, actually 12 to 9, yeah. 12 to 9 would be 90 degrees. Sorry. So 12, no, it's 45 degrees. Sorry. 90 degrees would be 6, right, from 12 to 6. And then from 12 to 3 would be, if you're going counterclockwise, Counterclockwise is backwards of the clock, right? If your big hand's on the 12 and you go from 12 to 9, that's 45 degrees. If you go from 9 to 6, that's 90 degrees. If you go from 12 to 3, that's 270 degrees. And then if you go from 12 to 12, that's 180 degrees. So if you go all the way around, it's 180 degrees. If you turn around, right, that's not doing a 180, that's doing a 90, right? Or actually, sorry. I'm foggy today, okay? So hang on, foggy today. So from 12 to 9 is 90 degrees, sorry. There you go. From 12 to 6 would be 180 degrees. From 12 to 3, I had right, 270 degrees. And then from 12 to 12 would be a 360.
There we go.
Okay, there we go. I got it right now. A little foggy. Must have been the flash bulbs over there in the pictures or something. All right, so the point of rotation is the central point around which a figure is rotated. So the point of rotation is what we're rotating around. Okay, that point of rotation. The line of reflection or reflection line is a line that is perpendicular bisector of the segment with endpoints at the pre-image point and the image of that point after reflection. So basically all these points are perpendicular to the line of reflection. Okay? So this is perpendicular to that line, these two are perpendicular to that line, and these two are perpendicular to that line. So all these points are perpendicular to the line of reflection, and this line of reflection cuts the space between these two figures in half. Okay? Cuts the space between those two figures in half. It's a bisector. We have corresponding sides. Corresponding sides are sides that have the same relative positions in geometric figures. Okay, relative position. So for example, these two sides here are corresponding sides. If you look at this triangle, this side matches up to this side, this long side here matches up to this side, and this short side here matches up to this side. As well as the angles. We'll do the same thing, and we're going to talk about that next. So in corresponding angles, the angles have the same relative position in the geometric figure as well. And it doesn't matter if the figure is rotated like this one is. This small angle here matches up to the small angle there. And if you notice, they have three lines on them. See how these three have, this angle has three half circles. This one has three half circles. That's showing you that those two are the ones that are supposed to be matching up. This one has one half circle on it. This one has one. And this one has two. This one has two. So they're showing you which one corresponds to which side, or which angle. Same thing with the sides. This has one dash, this has one dash, this has two, this has two, this one has three, this one has three. So they're showing you which ones are congruent to each other. All right, let's talk about dilation a minute. So a center of dilation is a fixed point in a plane about which all points are expanded or contracted. It is the only invariant point under a dilation. Invariant point. What do you mean by invariant point? When we talk about this, what do you think it means? A fixed point in the plane about which all points are expanded or contracted. It is the only invariant point under a dilation. What do you think they're talking about?
Where all the angles come to one point? All the lines go to one.
Well, certainly they do, right? They kind of have lines drawing through here, right? Lines drawing through here and lines drawing through here. But what happens to this point? Does this point move?
No.
This is the only point that doesn't move, right? So that's what they're talking about. It's another word for saying a fixed point, invariant point, right? That's the one that stays the same, doesn't change. Dilation factor. So a dilation of scalar factor K, scalar factor K. So when they talk about K, they're talking about a scale factor. What's a scale? What's a scale factor? What do you think that would be? Scalar factor. Well, maybe you couldn't figure it out by that. Whose center of dilation is the origin, may be written as this, okay? Multiplying K times the number, or X times K, and then Y times K to increase the scale. If the scale factor K is greater than 1, the image is an enlargement, a stretch. If the scale factor is greater than 1, you're making it bigger, right? If it's 1, it stays the same. If it's greater than 1, it gets bigger. What happens if it's less than 1? It gets smaller, right? It gets smaller. So if you have a model, who in here put together models before? Just one person, two people? Anybody put together puzzles? Anybody do a puzzle before? Okay. So on your puzzles, it has a scale factor, right? It's saying it does. You can read the box. All puzzles have a scale factor. And it may say 1 to 400. Scale is 1 to 400. That's 1 over 400. That means it's 1/400th the size of the original object it's a picture of. So if you do a puzzle and you put it together and it says that it's 1/400ths or 1 to 400 of the Statue of Liberty, that means it's 1/400th scale of the Statue of Liberty. It's smaller, right? It's not bigger. It's a fraction, 1 over 400. Same thing with models. It may be 1 to 10, it may be 1 to 100, but the models generally are going to be smaller. If you go to automotive industry and you're working on a scale model that you are putting together for a mock-up, right? For a mock-up on cars, they literally do clay and wood or plastic examples of the car they're going to build, but they do it on a 1-to-1 scale. Meaning, though, that if, even though it's a model of the one they're going to build, it's an exact size of the one they're going to build. It's a one-to-one. Okay? Sometimes they do it out of clay, sometimes they'll do it out of plastic, sometimes they'll do it out of other material. Yes, sir?
So the bigger the number, the smaller.
No, because 1 over 400 is smaller than 1.
That's what he said, the bigger the number, the smaller it is.
No, because 1 over 400 is smaller than 1. That number is smaller than 1.
Yeah, that's
It's
all.
not bigger than 1.
It's a fraction of
It's a fraction of 1. So the bigger the number,
The bigger the
the bigger the scale.
denominator. You
I'm
know
talking about like
what
models though. Like
I am
the
too.
smaller the model.
I am too.
Because
I think
the
he's talking
136 is
about
a bigger model. than
When you
the
talk about,
172.
so let's compare that.
I know
So
what you mean.
1 to 400 is larger than 1 to 700.
Mhm.
1 to 400 is larger than 1 to 700. So the smaller the number, the smaller the model.
The smaller the number, the bigger the model.
Yeah.
He's
For the
talking about
denominator.
for the
Oh
talking about the denominator.
So
Yeah, we're
one
Okay,
over
so-
I build my
100
models.
So, no, let's
is
look.
bigger than
So let's look at
1 over
this.
700.
We have one model that's 1 to 400. We have another model that's 1 to 700. Okay?
Which one?
So as a number, this is a fraction. As a number, this is a fraction. This model would be smaller than this model.
Yes.
Yeah,
Yes.
That's
we're
what
talking
we've been
about the
saying.
denominator.
But it's not a bigger number. It's a smaller
We're
number.
talking about the denominator if it's a
Okay,
bigger
but that's
number.
not what he said. So let's just clarify.
That's what he meant.
But-
That's what he.
But let's
That's what
clarify.
we've kept-
So again, the larger the number, the bigger the model.
5 guys.
This number is smaller than this number. 1/700th is smaller than 1/400th. Okay? So I just want you to clarify that.
Probably gonna want to delete this off of video.
When you have a number line and you have 0 here, 1/400th may be here, and 1/700th would be here. Smaller number.
Okay, but when I build my, like, the model companies, they say that, like, a 136 scale is bigger than a 172 scale.
That's true.
That's,
A 136
The bigger
scale
the
is
denominator,
bigger than a 1
the smaller
to
the
72nd scale.
model.
Yes,
Uh-huh.
yes. So the bigger the number, the bigger the scale.
The bigger
You gotta know
denominator
your
is the
fractions,
smaller,
right?
okay?
1/4 is smaller than 1/2, right? 1/4 is smaller than 1/2. So 1/72 is smaller than 1/32.
Okay.
Did
Yeah.
you understand
So just
what
clarify
he
that.
said?
All right, so you got this in your notes? Sorry, we didn't mean to get sidetracked there.
It's okay, no one got it. I don't understand what we're talking about.
Guys, not necessary.
Huh.
All right, so transformation. What exactly is a transformation, okay? What happens to its shape, what happens to its size, and what happens to its orientation, okay? So we have several different types of transformations we're going to deal with. The first one is a translation. So a translation is when every point of the preimage moves in the same direction by the same amount to form an image. A translation is also referred to as a slide, and we almost always refer to it as a slide. A translation creates a similar and congruent figure. So it's isometric, right? It's isometric, it has isometry to it because it does not change size and shape. So the angles remain the same, measurement. The size remains the same all around. And the orientation remains the same. The figure is just moved from one location to another, and all the lettering remains the same. all the lettering remains the same. Now, when you're looking at this one, because we haven't talked about this yet, when you have a pre-image, the pre-image is labeled ABC. ABC. The image is labeled A prime, B prime, C prime. And it has this little tick mark right above the C, okay? Right above the C, right above the A. It's got a little tick mark right above the B, okay? That means, without looking to tell or to determine what they said was the pre-image or the image, stop flicking your pen for me, please. Looked at you twice. Besides them telling you which one is the image and which one is the pre-image, you can tell by the markings on the figures. If you don't have those tick marks, that's the beginning. That's the original figure. That's the pre-image. If they have the markings with the letters, that tells you that that is the image or the copy of the original. When you're talking a reflection is a transformation in which each point is mapped onto its reflection image over a line or plane. A reflection creates a similar and congruent figure. Again, a reflection is isometric. It maintains all the congruent sides and congruent angles. It doesn't change in shape. So the angles remain the same, the size remains the same, but now the orientation is reversed. Letter order is not preserved, so it's not in the same order. It's reversed than what it was. All right, let's go on to rotation. So rotation is a transformation in which every point of the pre-image is rotated by a given angle about a point. So you're rotating around a particular point by a particular degree in a particular direction. So when we talk about rotations, we're going to talk about two types of rotations. We're going to talk about a clockwise rotation, a CW rotation, right? And a CW rotation or a clockwise rotation goes the same direction as a clock. It turns to the right. Then we're going to talk about counterclockwise rotations. And counterclockwise rotations, go the opposite direction of a clock. So they go to the left, not to the right. The angles remain the same, the size remains the same, and the orientation remains the same. So the figure is still labeled the same way. So the last one here is dilation. So dilation is a similarity transformation, meaning the figures turn out to be similar. There's only one type of dilation where you maintain its congruency, and that's when it's a scale of 1 to 1. If I have a scale of 1 to 1, it doesn't change anything, it stays the same. But any other scale factor other than 1 to 1, it's either going to enlarge if the scale factor is greater than 1, or it's going to reduce if the scale factor is less than 1. Angles remain the same, so all the angle measurements still stay the same because it's a similar figure. But the size increases or decreases depending on the scale factor, but the orientation does remain the same. Okay. All right. Questions on any of that so far? I know we spent a little time on those dilations, probably more than we should have.
Do you want this one? What can I have? Angle of rotation.
Please go. Yeah, two.
Huh?
No.
Well, I gave mine.
So what we're going to do is we're going to start with this first problem up top. Down here in this bottom, you're going to see all this stuff: rotation, translation, reflection, transformation, perpendicular bisector, axis of reflection, center of rotation, angle of rotation, image, invariant point, pre-image, orientation, parallel, isometric, and mapped. Okay, you have also this A prime, perpendicular bisector, and rotation. Now mapped, we didn't talk about mapped. Okay? When we talk about mapped, we're talking about taking one figure, or what's it going to take one figure and map it onto itself. Okay? That literally just means, what is it going to take to move this figure on top of that figure? Exactly. Get it to go from one place exactly on top of the other. Literally, if you were going to pick it up, move it, and set it on top of the other. That's what we talk about when we say mapped. Okay? What is it going to take to map this figure onto the other? Okay? To get it to move from one place on top of the other. Okay? So the first thing we're going to do on this one, we're going to graph the line y equals x and label it M. Who knows what the line looks like that is y equals x? Anybody?
The middle?
What's the line look like?
It goes through 0, 0, and just, it's 1 for 1.
Okay, it's a diagonal line, right? It's a diagonal line, and it goes through the point of origin. So that means if x is 0, y is 0. Tom, you got a pencil? If x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 2. Because y is the same thing as x. If x is 3, then y is 3. And then you just take your straight edge, any kind of straight edge for right now, the binder, whatever it happens to be, and you're just going to take and you're going to draw that line through those points, and you're going to label that line M. Just any kind of straight edge, whatever you got. Binder, ruler, whatever the case may be. Okay. Now you're going to graph the line y equals x plus 2. X plus 2. So again, y is going to equal whatever x is plus 2. So if we start at 0, if we say x is 0, what is y?
2. 0.
If we start with x is 0, what is y? 2. 2. So if x is 0, y is 2. If x is 1, what is y?
3.
3. If x is 3 or 2, what is y? 4. Okay. Now you're going to just graph that line. And that line you're going to label N. Okay, you're going to label that line N. That should be brighter than that. All right. So how are those two lines related?
Parallel.
They're parallel lines. Okay.
They're translated.
Are they a rotated line? Are they a translated line?
Yes.
They could be, right? They could be translated just means to slide, right? So this line could just be a slide over to here and it wind up in the same place. So if things are parallel to each other, we can just slide them over. Could it be a reflection?
Yeah.
Could be a reflection too, because if I reflect it across this point right here, to this point right here, you can say it's the same distance from here to here as it is from here to here. So we could reflect across a point and it would just fall on top of each other. So that could be either a reflected line or it could be a translated line. Okay? Or it could be a translated line. Could it be a rotated line?
Oh, I don't know, this is tricky.
No.
Probably not, and,
That's like
well, it could be, if you rotate it about a point, okay? It'd be hard to figure that one out, but you could probably rotate that. Would it not look the same when we rotated it? If we turned it? That doesn't look the same, does it?
No.
No, because they're going the wrong direction. That doesn't look the same because they're in different areas, right? That doesn't look the same. Could it be a 360-degree rotation? So, could it be a rotation? Well, it could if we rotated it 360 degrees. Could be if we rotated it 360 degrees. All right. What kind of line is y equals 3?
That's just a point.
This is a line.
Y equals 3 to
This is an equation. What kind of line is y equals 3? These are special cases, right?
Isn't it
Y equals 3, x equals negative 3.
vertical?
Well, it's close to vertical, only it would be horizontal,
Oh.
right? When it's y equals, it's going to be horizontal. When it's x equals, then it's going to be vertical, okay? So when you have y equals 3, they're saying there's a line that goes through y equals 3. 1, 2, 3, this point right here, and it's going to be a horizontal line. Special cases. So there we have y equals 3, or at least it's close to that. You're going to label that Q. And then you're going to look at x equals negative 3. And again, that we just talked about is a vertical line. So you're going to graph x equals negative 3. And you're going to label that one Q.
R.
What kind of
Q.
Q and R? Well, let's call that one, well, I need the other one Q, didn't I? So yeah, let's make this one. How are those two lines related?
They're perpendicular.
Okay, so they're perpendicular. So they're meeting at 90-degree angles. Okay, all right. Now graph one more. Graph y equals negative x plus 2 and label it S. Label it S. So if x is 0, right, then y is 2.
That's a negative.
If x is 0, y is 2, right. Well, negative 0 is, there's no such thing, right?
Yeah.
So we got a point right here. If x is 1, then we have negative 1 plus 2. And negative 1 plus 2 would be what? If x is 1,
That's 1.
if x is 1, this would be 1, right? What about if x is 2? If x is 2, then you have negative 2 plus 2, y would be 0. In your line would go that way. And then this would be, what did it say to label this one? Label this one S. And then it said to compare lines N and S. And what do you get again?
Perpendicular?
Yeah, they look perpendicular, don't they?
Oh.
Yeah, better look at it that way.
Oh.
It's a better look at it that way. Kind of looks not perpendicular from the top, but when you turn it, it does. All right.
Question.
So, yeah.
If you rotate at that one point, like where they're both touching, would that just make it mapped or?
You mean rotate it about that point?
Yeah.
You can map one on the other by rotating about that point, yes. Yes, sure could. Because your rotation point just kind of stays the same. So it's kind of like putting your pencil down on it, right? and then turning the figure, right? That's kind of what rotation would be. When you're rotating about a point, it's like that point stays still, and everything rotates around that.
So
Yeah, you can do that.
when it says how are lines N and S related, can we put rotation?
It's just looking at